As we know, quantum mechanics is all about orthonormal functions. The wave functions that we use are almost always when we talk about exact solutions, they either form an orthonormal basis or they are made up by linear combinations of functions that form a complete orthonormal set. So, it makes sense at this stage of our discussion to see what happens when we express trial functions as a linear combination of orthonormal functions. Okay? And we know about the properties of orthonormal functions that we have studied in the past. Great. So, what we will do is we will do that and we will actually come back to particle in a box with a little bit of twist when we talk about orthonormal functions. So, let us quickly recap what we learned in the previous module about variational calculation that we performed for particle in a box. There we had represented the wave function as C1 F1 plus C2 F2, where F1 was x into 1 minus x, F2 was x square into 1 minus x whole square. Are they orthonormal? Okay, you figure out, but they are definitely not the functions that we get by solving the Schrodinger equation exactly that we have done towards the beginning of this module of this course. So, and this is the Hamiltonian minus h cross square by 2m d2 dx2. So, what we did was that we wrote this secular equation and then we found out the expressions for all of these matrix elements H11, H12, H21, H22, S11, S12, S21, S22. And then knowing these expressions and substituting E dashed for Em by h cross square, this secular determinant simplified into this form 1 by 6 minus E dash by 30, 1 by 30 minus E dash by 140, 1 by 30 minus E dash by 140, 1 by 105 minus E dash by 630. That determinant is equal to 0. This expands as a quadratic equation which has two roots 51.065 and 4.93487. Of course, out of these this is the lower value, that this is ground state energy. And then what we did is we wrote this in terms of h cross square by m and we compared this minimum value that we got of energy with the exact value of energy that we got earlier, and we see the agreement is really good. If you go to the 6th place of decimal, there is a difference between the calculated minimum value of energy and the calculated exact value of energy that we got earlier. So, we are good here, but then just because it has worked nicely for particle in a box does not mean that it will work if we use arbitrary wave functions for more complicated systems. We want to simplify it. That is why we want to talk about orthonormal basis. So, in this linear combination that we have, we want to write these fn's that are members of a complete orthonormal set. Of course, even before going there, if we simply write this expression, then no matter whether fn's are orthonormal or not, you will get this kind of a secular determinant. Okay? Last time we had just 2 by 2 determinant, this will be n by n determinant, that is all. And we will get n roots, we have to evaluate the integrals, and the one with lower energy will be the ground state. Okay. Now, when we use orthonormal basis, and we just touched upon this before closing the previous discussion, the expressions become simpler, and expressions become simpler for the simple reason that Sij integral of fi star fj over all space, all function space is equal to delta ij. We know that when I is equal to j, then you get 1 provided f1, fi and fj are normalized, and of course we are saying that they belong to an orthonormal basis set. So, they are normalized, and if I is not equal to j, then well, once again remember they belong to an orthonormal set. So, if I is not equal to j, then this integral becomes 0. So, what happens to this determinant in that case? H11 minus Es11, this S11 becomes 1. So, this becomes H11 minus E. This 1 2 position S12 becomes 0. So, the second term vanishes completely, you are left with only H12, and that happens for all the other elements all the way until H1n, this S1n also becomes 0. When you go from top to bottom in the first column, all these second terms vanish because they are of Sij type. The 2,2 term, what happens there? S22 is equal to 1, so you get H22 minus E. So what we see is that the diagonal elements are all like Hii minus E, off diagonal elements are all Hij, Hji, that kind of thing. Okay. So this is what you get, H11 minus E, H12, H13, so on and so forth until H1n. Then when you go down, H11 minus E, H21, H21, so on and so forth until Hn1. Diagonal elements Hii minus E, that is what you get. And then already the expression has become simpler. What about H12 and H21? Can we say that they are 0? Yeah, actually we cannot. Okay. If you think that they are 0, it is not necessarily correct. We are going to encounter a situation where they are 0, but it is not, that is not the general case. Why? Because if you write this Hij, any I, any j, if you write Hij, that is equal to integral Fi H Fj. The problem is, see, Fj usually would be the eigenfunction of the Hamiltonian of the system that is solvable exactly. Generally that is what we choose. So this Hamiltonian is different, right. For example, well, we have not taken that example yet, when we take it we will see this Hamiltonian is not usually the Hamiltonian of the system for which we can solve Schrodinger equation exactly, right. Even then we can write the Hamiltonian. So it is not necessary that Fj is an eigenfunction of this Hamiltonian, right. So we will not get a constant coming out of the integral always. Sometimes we can have special cases, we will see. So what we will do is we will keep Hij for now, and we will set this Sij for I not equal to j to 0, and we get this kind of a secular determinant. Now we take this example. We go back to our particle in a box, but we include in it a twist, or rather a bend, if you want to call it that. What is that bend or a twist? We say that here potential energy is not 0. However, we see that the potential energy is x dependent. For x lying between 0 and L by 2, okay, half of the box, the potential energy is V1 multiplied by x, where V1 is a constant. For the other half, for x ranging from L by 2 to L, it is V1 into L minus x. Okay. What happens at x equal to L by 2? If you take the first expression, you get V1 into L by 2. If you take the second expression, then also you get V1 into L by 2, right. L minus L by 2, that is L by 2. So there is no discontinuity in the function as such, there is a discontinuity in slope. What does the potential energy look like then? Let us say this is my particle in a box. For the first half from the left, your potential energy will be a straight line with a positive slope, right, V1 into x. For the second half, it will be a straight line, but with a slope that is negative, equal in magnitude but negative. Now in this system, let us use this trial function phi of x is equal to C1 psi 1 x plus C2 psi 2 of x. What are psi 1 and psi 2? Remember what we want to do? We want to use an orthonormal function, and while using orthonormal function, it makes sense to use orthonormal eigenfunctions of the Hamiltonian of the system for which we can solve Schrodinger equation exactly. Then things will start making sense. You want to talk about particle in a box, the orthonormal set that you use, at least to start with, it makes sense to take the wave functions of the Hamiltonian for a particle in a box in which the potential energy is 0 as long as the particle is inside box. And we know that those solutions are something like this: psi n of x is equal to root over 2 by L sin n pi x by L. N, as we know, ranges from 1, 2, 3, 4 all the way up to infinity. That is those are the quantum numbers. Okay. So, remember, when I say psi 1 of x, I essentially mean n equal to 1 put in this expression. When I say psi 2 of x, I mean n equal to 2 put in this expression. Okay. So, this is the formulation of our problem. As usual, I am not going to solve every step. In fact, in this case you also do not need to solve every step, you need to understand the logic. If you can solve it, then it is even better, but as long as you understand the logic, you do not have to remember the final expression. Please remember that. These are not things where you need to know the formula or anything. Okay. You need to know only the very basic formulae that we already know by now. Please do not try to remember the results, it makes no sense at all. Okay. Try to understand the logic. Okay. So, what will we do now? We know what the potential is, we know what the trial function is, and we have expressed it as a linear combination of the orthonormal eigenfunctions of the Hamiltonian of particle in a box for which v equal to 0 as long as the particle is within the box. Okay. Now, we want to evaluate the matrix elements one by one. I will show you some steps of H11. How do we write H11? Integral psi 1 x star. In this case, of course, star is redundant, it's just psi 1 x is fine, because psi 1 of x is fine because it is a real function that left multiplying Hamiltonian operating on psi 1 of x. Let me, for the record, we will refer to it shortly, but let me even now write it once. What is this Hamiltonian? What is the Hamiltonian for your particle in a box for which v equal to 0 inside and v equal to infinity outside? You just have the kinetic energy term, is not it, minus h cross square by 2m, well 1D box, so I might as well write d2 dx2. That is for the particle in a box that we have studied earlier. In this case, particle in a box with a twist, we have an additional potential energy term which itself changes its expression at x equal to L by 2. So, to write the general expression, I will write that Hamiltonian is minus h cross square by 2m d2 dx2 plus, let me just write u of x. Depending on what x is excuse me, depending on what x is, we are going to use the appropriate expression for u of x, the potential. Okay. So, this is what we will use depending on the value of x. Okay. Of course, we are going to get two terms then, is not it? When we expand this integral, first of all there are two terms here, and secondly even this second term is different for different ranges of x. So, I have to write two integrals, one with limits from 0 to L by 2, the other with limits from L by 2 to L, so that we can write this analytical form of u of x. So, this is what I will write. 2 by L, where does 2 by L come from? Well, psi 1 psi 2, remember psi, well in this case both are psi 1. So, root 2 by L root 2 by L, so I will take root 2 by L outside, then integral between limits 0 to L by 2 sin pi x by L multiplying the Hamiltonian that we have written here. In this case u of x is substituted by v1x because I am integrating only up to L by 2, that operating on sin pi x by L dx. Okay. What will the second integral be? Same thing, except well similar, except the limits would be from L by 2 to L, and instead of v1x here I will write v1 into L minus x. Okay. This is what it is. So, I have written down the expression for H11. Alright. What do you get? What do you get if you try to say expand the first integral? Well, that is the final answer. Let me write the first integral. So, here if I take this sin pi x by L minus h cross by 2m d2 dx to sin pi x by L, and what I will do is I will bring this here also, root 2 by L here, root 2 by L here. So, this first one I can write it as I1 here will be equal to integral essentially psi 1 of x, well do not forget the limit 0 to L by 2. This one is Hamiltonian. Okay, since we know perturbation theory already, I will use the language of perturbation theory here. I will write 0th order Hamiltonian. 0th order Hamiltonian means the Hamiltonian of a particle in a box in which potential energy inside the box is 0. Okay. So, you can think that this is the 0th order Hamiltonian and this is the first order correction. Okay. So, I will just write like this, operating on psi 1 of x dx. Now, you already know what h0th operating on psi 1 of x is. That is basically the left hand side of Schrodinger equation for n equal to 1. So, it will be your E1 multiplied by psi 1 n, and for particle in a box where potential energy is 0, what is E1? h square by 8 pi square m, is not it? Yeah. If L equal to 1, if L equal to L, then it will be L square. Okay. So, this turns out to be just the energy, and then you integrate from, so this is equal to something like I will write epsilon 1 integral 0 to L by 2 psi 1 of x whole square dx. So, now tell me what is integral of psi 1 x whole square between limit 0 to L by 2. If I had integrated from 0 to L, what would it have been? It would have been 1 total probability. So, 0 to L by 2 for the symmetric wave function here, that is going to be half, is not it? So, this is how you expand. What about the second one? Second term arising out of the first part here, it will be V1 will come out and then you will get integral 0 to L by 2. Maybe I will write, I will erase all this and I will write. Okay, just erase everything. What I am saying is I take root over 2 by L sin pi x by L and I am multiplying it by V1 x, then again sin pi by x by L. Will you agree that, okay, I will call it I2, I2 will be equal to integral 0 to L by 2. I can write again psi 1 as we discussed earlier multiplied by x multiplied by psi 1 dx, and V1 will come out, is not it? V1 is a constant, remember. So, this will be V1 integral 0 to L by 2 x into sin square pi x divided by L dx. Does that ring a bell, or does this ring a bell? If I only change the limit from 0 to L, if I only change the limit from 0 to L by 2 to 0 to L, then this integral would be your average value of position. Here I am just integrating from 0 to L by 2. So, we know how to solve this integral using integration by parts. So, that is what one has to do. So, I am skipping all the steps here, but I have told you how to go about it, and well, I would encourage you to do this by yourself. When you do that, and then when you do when you perform a similar treatment to the second term that is there, then the final result that I will show you is this h square by 8 ml square. Remember what h square by 8 ml square is? H square by 8 ml square is essentially the energy of the particle in a box when potential energy inside is 0, potential energy outside is infinity. Okay, alright. So, that is what it is, and the second term arises out of well, I will call it the second term because I have written it as V1 into L multiplied by something that arises from the second terms of these integrals. Okay. If you do it, it is a little long, but it is definitely not undoable. Okay. So, this is the result we get. So, this here is our H11. H12 and H21 turn out to be 0, and we will discuss little later why it is that they are equal to 0. Remember, they are not necessarily equal to 0, but we will prove that they are equal to 0. H22 turns out to be h square by 2 ml square multiplied by V1L by 4. This h square by 8 ml square, that is energy of n equal to 1, right. So, I think I have written it later, but in case I have not, I will write it like this. This is epsilon 1. Do you agree with me that this is epsilon 2? What is epsilon n? I will write here is equal to n square h square by 8 ml square, right. So, if n equal to 2, then this becomes 4, 4 by 8 is half. So, that is how you get the 2 in the denominator. So, this is very nice, is not it? The first energy that we get H1, well, the first matrix element that we get, that is essentially the energy of particle in a box for V equal to 0, plus now again remembering our remembering what we learned in perturbation theory, plus we can say a correction term provided V1 is very small. H22 is energy of the second energy level plus a correction term provided V1 is small, and the corrections are not exactly the same. Here it is V1L, well, for H22 it is V1L by 4, for H11 it is V1L by 4 plus 1 by pi square. Okay. We will see how this is important, okay. But let us go ahead and finish our discussion. The secular determinant we get is this, okay, and it is very nice because it is a block factorized determinant. Since H12 into since H12 is equal to H21 is equal to 0, we get a block factorized determinant, and block factorized matrices and determinants are lovely because now see the solution becomes so easy. So, what happens then is this is H11, this is H22. Ideally you would have to write H11 into H22 is equal to 0 minus, well, H11 into H22 equal to 0, that is what we get. If we did not have non-zero off diagonal elements, then it would be H11 into H22 minus H21 into H12, and you would have to solve whatever equation you got. Now, H11 into H22 equal to 0 directly gives you H11 equal to 0 or H22 equal to 0, right. So, you do not have to even go into a quadratic equation. When H11 equal to 0, I simply get E equal to h square by 8 ml square plus V1L into 1 by 4 plus 1 by pi square. So, this thing that we get here is really one of the roots for energy. So, what we see is that one of the solutions is the energy for h equal to for n equal to 1 plus a correction term, that is one of the roots. The second root you get by equating H2 to 0 is E equal to h square by 2 ml square plus V1L by 4. So, once again energy of n equal to 2 plus a correction term. That is very nice. So, we know that these two are the energies of n equal to 1 and n equal to 2 for the regular particle in a box that we have studied earlier, right, and that is really very nice. So, whatever energy we got earlier plus some correction term. Okay. So, that is the advantage of having block factorized determinant. We have got the two roots, which one is lower in energy, which one is higher in energy. Most likely this is lower in energy, yeah, unless this V1L into 1 by 4 plus 1 by pi square, this is really large. If that happens, then well, but then that will add here also. So, this is the lower energy, I think we can say that with sufficient confidence. Okay. Now, if you did this same treatment from perturbation theory, which we are not doing explicitly, you would get the same result. Okay. And we should be willing to believe that also, because the result is definitely in line with what one gets from perturbation theory. The 0th order energy plus a first order correction, right, that is what you get. So, these two theories are in agreement with this. The important thing here is that there is no contribution of psi 2 in ground state energy. Ground state energy is the unperturbed energy, now if I can say, plus a correction term. Okay, if this is small, it is nowhere close to the energy of the second level, and that happens because these H12 and H21 are 0. So, now we better discuss why is it that H12 or H21 must be equal to 0 in the case that we have discussed. So, let us write it out. H12 is integral 1 to L, and now I can write 1 to L because I am writing the general expression for u of x. I am not writing V1x or V1 into L minus x. Depending on the range I choose, I can substitute u of x as V1x or V1 into L minus x. So, this is the general expression we get. Of course, we can break it down into two terms, and when we do that, in the first term again what do I have? I have psi 1, then Hamiltonian, unperturbed Hamiltonian operating on psi 1. So, of course, I will get the unperturbed Hamiltonian operating on psi 2, not psi 1. I am not talking about H11 anymore, I am talking about H12. So, the eigenfunction that we have of the Hamiltonian gives me an eigenvalue of E2. When the unperturbed Hamiltonian operates on psi 2, I get E2, which is constant, comes out of the bracket, integrate from 0 to L psi 1 of x multiplied by psi 2 of x dx. What is that? That is definitely equal to 0 because psi 1 and psi 2 are orthogonal to each other. What about the second integral? Integral 0 to L psi 1 of x u of x psi 2 of x. Actually, to evaluate it, there is no need for me to write the explicit form of u of x, because one thing I know for sure is that it goes up and goes down, remember, it is like a triangle. So, it is symmetric with respect to the midpoint. So, the psi 1 of x is symmetric, that we know already, it is a sine function that does not go through a node. Psi 2 of x is antisymmetric like this, u of x is symmetric. And now we have studied this when we talked about particle in a box, allowed transition, disallowed transition. What happens when the integrand is a triple product of two symmetric and one antisymmetric functions? The integrand is antisymmetric, and we know by now that an integral of an antisymmetric integrand is equal to 0, is necessarily equal to 0. So, both the terms of H12 or H21 for that matter would be equal to 0. That is why H12 and H21 is 0 in this case, and that is what makes life very simple for us. This leads to this interesting observation that psi 2 of x makes no contribution to ground state energy, only psi 1 of x makes the contribution to it. This is a general, this is sort of a subset of a more general phenomenon, that when we express our trial wave function as a linear combination of orthonormal functions, then the functions with higher energy have lower contribution to the ground state. Okay. So, now let us write again using the notation we learnt in perturbation theory. Hamiltonian is 0th order Hamiltonian plus first order correction. Phi, this is what we have written in our earlier treatment of variational treatment, phi equal to C1 psi 1 plus C2 psi 2. And now we are saying that these psi's are eigenfunctions of the 0th order Hamiltonian with eigenvalues Ej 0th. So, the secular equations we get in this case, what would they be? They would be H11 minus E, H12, H21, H22 minus E, what we have learnt earlier. What is HII? Instead of H11, H22 separately, I will just do HII. This is what HII is, 2 terms. The first term I hope you can see without much hassle, we have done it just now. First term is Ej 0th multiplied by integral psi I star psi I over all space, which will be equal to 1, plus integral psi 1, well psi I first order correction to Hamiltonian operating on psi I. So, what is this? The second term? The first term of course is Ei 0th uncorrected energy. Second term, as we have learned in our perturbation theoretical treatment, this is the first order correction to energy. So, we get Ei 0th plus first order correction to energy. So, that is what we use and this is what we get. And then if you solve the quadratic equation, I am jumping steps here, and if you use a power series expansion, then this is the approximate result you get. You will get there will be more terms, but they will make progressively lower contributions. We get E1 equal to E1 0th plus first order correction to E1 plus this H12 square divided by E1 0th plus E1 first minus so on and so forth. If you now remember the earlier problem of particle in a box with that triangular potential, you will remember that H12 is equal to 0. There it automatically follows that E is equal to the 0th order energy plus the first order correction. For other general solutions, if you work in the regime that the energy levels are sufficiently, the spacing between the energy levels, successive energy levels is sufficiently large. If you work in that regime, which is a reasonable approximation, a reasonable thing to imagine, then this difference is going to be large. If this is large, then this term will become small because H12 is never very large. So, then approximately you get E equal to E1 0th plus E1 first. So, the higher terms do not even contribute to the ground state energy. Okay? So, that is what we have. And now to close this discussion, let us just introduce the general case. We are talking about linear combination of orthonormal wave functions, and what we have said so far is that it is the coefficient that is the variational parameter. That is not necessarily the case. I can also have variational parameters within these orthonormal functions themselves, the f's themselves. Okay? For example, for hydrogen atom, we can write the function like this, sum over j Cj e to the power minus alpha j r square. So, this function here is similar to the 1s wave function, with the exception that this coefficient in the exponent is also a variational parameter. So, 2 variational parameters gives me greater flexibility, and of course, you can play around with number of terms. So, once again remember hydrogen atom of course is exactly solvable, but if we do a variational calculation using this kind of parameter, this kind of a linear combination, and if we keep increasing the number of n's, what we see is this. If you use n equal to 1, this is the energy that you get minus 0.424413. If you increase the numbers, go from 1 to 2, it becomes lower, to 5 even lower, 16 minus 0.49980. And now the exact calculation, let me remind you, in terms of what we have given here, mu e to the power 4 by 16 pi square epsilon 0 square h square, the exact calculation that we got earlier is minus 0.5. So, now when you increase the number of terms to 16, you get very close to the exact solution. Okay? So, what we learned from here is that in the general case, if you increase the number of terms, you get closer to the energy, and that is by using the power of variation theorem, upper limit theorem. One thing to understand here, if we include the variational parameter in the functions themselves, is that the secular determinant is complicated, right, because the variational parameter is also there in the functions. So, in fact, we will not be able to get an analytical solution like what we have been getting so far. You have to solve this numerically. Put in number, see what solution that you get, change the number, see what solution that you get, and you need different kinds of algorithms, and this opens up the field of computational chemistry. I think I said this opens up field of computational chemistry once earlier. Well, this really takes us into the domain of computational chemistry, but let us talk a little more about this a little later. The other thing that happens here is that now see we have slowly started going away from the exact solutions. We have changed the exact solution 1s orbital by this introducing this variational parameter a little more significantly than what we have been doing so far. So, eventually we will reach a situation where you perhaps even do not have to start from the exact solutions, any kind of orthonormal set will do, okay, but let us wait for that. For now we close this discussion, and finally we are now ready to resume our discussion of many electron atom. The discussion will be on helium.